Right. Iterative methods. Introduction. Many equations can only be solved graphically or by methods of successive approximations to the roots, called iterative methods. And in actual fact, your calculator is using iterative methods to do many of the things it does, including finding the square root of a number. Because it doesn't have a table stored in memory of what the square root of every single number there ever was is, so it uses its very fast processor to go through the iterative methods that we're going to do today to more decimal places than we're going to do. Okay? But ultimately, if it's filled the calculator screen up with its, 10, 12 digits accuracy, then it can stop iterations after that because it's not going to get any more accurate. Okay? So we're going to look at one method today and another one next week. One is the bisection method, and the second one is the Newton-Raphson's formula method. Right, and we're going to make comparisons of using the two for particular functions. Okay, so next there's a blank page because with no calculator yeah, I did, yeah. Square root of 9. What is the square root of 9? 3. What's the square root of 7? Without a calculator. 2.72. Why do you say that? Is it between 2 and 3?
Well, I would say that just from looking at it, obviously isn't, but if the square root of 9 was 3, then the square root of 4.5 could possibly be 1.5.
First of all, the square root of 9 is 3 because 3 times 3 equals 9. That's what it's about. That's going back the other way. Yeah. So saying this, if you're doing an estimate, 2 times 2 equals 4. 3 times 3 equals 9. So the result of the square root of minus 7 is between 2 and 3. So you're right in that. Yeah. So how are you going to take that further to get more decimal places? Yeah. What is 2.5 times 2.5? So that what would you say the square root of 7 is between now? So where would you go with it next? Something that you can multiply together. Two and 3/5. So what's 2 and 3/5 times 2 and 3/5 then, Nathan? What? What's 2 and 3/5 times 2 and 3/5 in your head? 2.6 times 2.6. What is the result of that? So where's your estimate of square root of 7 now? Between 2.6 and 3, isn't it? Because we're still underneath. Next guess. I'll give you that at 7.0225. Yeah, so we are between 2.6 and 2.65. And we could go on. But just trying to demonstrate a rough method of how you might work out, and you could do that, the multiplications on a piece of paper, to estimate to a given number of decimal places the square root of any number through estimation. Yeah? The bisection method is formalising that process into a definite process that you can, once you realise how it works, do very easily with a spreadsheet. Okay? And you can see that because it's iterative, you can quite easily write a programmed function if you know how to do that in a particular software to go through that process. You do an iterative method, is what your calculator does. So, making an initial estimate. We need to know where to start. So, each of the iterative methods requires this an estimate to the root to be made. One way is to take a graph of the function manually or using graph plotting software. The other is to use a functional notation method. Okay, so if, for example, we want to find, this is a graph of y is equal to x squared minus x minus 5. And we can see that it's got two roots. The roots are the values of x, where y is equal to 0 in this particular case. So it indicates that we've got a positive root between 2 and 3 and a negative root between minus 1 and 2. Yeah, so in terms of, if we're going to find this positive root here, this one, we're going to need the function at values above and below. What we're doing is we've got, look at the function when x is 2. The result is that it's equal to minus 3. And we look at the function when x is equal to 3. And we get the result 1. That says that there's a change of sign, and therefore we've got one positive result, one negative result. We must be crossing the x-axis. Because y, in the first example, when x is 2, is negative down here. And when x is 3, the result y is positive up the top here, so up here somewhere. Okay? 3 is there, so it's about where's 1. Alright? So, moving on from that, what we then do is we go through a process. So, bisection method. Remember what we're doing, we're going to look for changes in sign as we try different guesses. So, we're going to use the bisection method to find the positive root of the equation 5x squared plus 11x minus 17 is equal to 0. So that is the function graphed. We're looking to find the value of this positive root here. Yeah? And it looks as like it's around the area where x is equal to 1. Yeah. So when x is equal to 0, we get a negative result, minus 15. So if we put 0 in here, that bit's 0, that becomes 0, that bit is minus 17. So it's negative. If we try x is equal to 1, we get 5 times 1 squared is 5, plus 11 is 16, minus 17 is minus 1. We're still negative. So the third guess is to go up to x is equal to 2. We end up with 5 times 2 squared is 20, plus 22, minus 17 is plus 25. We've got a change of sign from negative to positive. So the root must lie between x is equal to 1 and x is equal to 2. Yeah? Are you all happy with that so far? We've got two different guesses, and one gives, when we put those guesses into the function, we get a change from negative to positive, or positive to negative. If that parabola was the other way up, as we went higher in x value, we'd go from positive to negative. So it's the change of sign that's important, not that it goes from negative to positive. So it could go the other way. Alright? We need a good first guess, because it's important that we don't go too wide and actually bring in two different roots, and we find that one instead of that one. So we need to make sure our initial guess is in the right place. Yeah? So, second step is to find the midpoint between the two limiting values. So the midpoint between the first two guesses. So we've got guess 1 was 1, that's where the result was negative. Guess 2 was 2. Divide that in half. Halfway in between is 1.5. So we put 1.5 in place of x in the function, and we get a result of plus 10.5. We now know that the result is between x is equal to 1 and x is equal to 10.75, because when 1 is negative, minus result, plus result. So our best guess now is 1.5. We're looking for 3 significant figures, so we haven't even got that yet. You're all happy that our current guess is this value, 1.5. So you find the result of that, and then that's between the nearest positive and negative values that we've got. So what we do then is bisect again. So we go halfway between the 1 and the 1.5 to 1.25. We put that in the function, and we find the result is plus 4.5625. Okay, we now know that the root is between 1 that gives us a negative result and 1 that gives us a positive result. So we are between 1 and 1.25. Yeah? So what we now do is go halfway between 1 and 1.25. So we do 1 the fifth guess is equal to 1.25 over 2 equals. What's the result of that? Yeah. So that's our new guess. Yeah. And then we go f at 1.125 is equal to 5 times 1.125 squared plus 11 times 1.125 minus 17 equals. Yeah, what you can't do here is you can't start stripping down to that two significant figures. We need to keep the results here up, so the reason will become clear in a minute. We're looking for a result to 3 significant figures, remember. Alright? We'll take that. 5 decimal places will be plenty. Okay? What we want to start doing is recording this value just to the right to 3 significant figures. So what's that to 3 significant figures? 1.13. Yeah? Carry that process on. What you're looking for is for that number, i.e. the guess to 3 significant figures being the same for a second time. Yeah? So let's say you get a result where that's 1.5 at 1.12, and then the next time are still 1.12 to 3 significant figures. You stop. That's your route to 3 significant figures. Carry that process on, see if you can find me the route to 3 significant figures. You've got to keep going until the guess to 3 significant figures is the same twice. Remember what the original question is asking you? It's asking you to estimate this route correct to 3 significant figures. And because you're doing these iterations, you're getting closer and closer to the actual value. If you only want it the 3 significant figures, there's no point in doing more iterations and adding more accuracy when you've already got the same result twice. Yeah? So that's how it works. When you get to there, there's a sign change. So the bottom end of your range of guesses becomes 1.03125 instead of the 1. Yeah, so you now got to add those two numbers together and divide by 2 to go even more. Right. I'll just go through that, okay? We already had done a couple of iterations. We had a guess that was 1.125, rounded to three significant figures, 1.13. Put the 1.125 into the function, still got a positive result, so we're between 1 and 1.25, gives us a new guess of 1.0625, which rounds to 1.06. Put the 1.0625 in the function, we still get a positive result, so we're lying between 1 and 1.0625. Use those two numbers, find another new guess, 1.03125, which rounds to 1.03 for three significant figures. When we put that value in the function, we get a negative result. Our sign has changed. We've gone below the x-axis. So our new bottom guess, a bottom limit, has changed from 1 to 1.0325. There. We find another new guess, 1.04, which rounds to 1.05 to three significant figures. And we put that 1.046875 in the function. We still get a negative result. So we've got another new bottom limit. Yeah. We then find another new guess, 1.054685, which rounds to three significant figures to 1.05, the same as the previous one. Therefore, we stop, because we're never going to get more accurate than having that result twice to three significant figures. We can stop. How many iterations have we had from the start? We started off on this problem here. We've done the first one. Find the second guess at 1.5. Yeah. Third guess, 1.3, fourth, 5th, 6th, 7. Okay? 7 iterations to find the root of three significant figures. Okay? Yes, it is a bit time consuming. Okay? What you're going to find next week is Newton-Raphson's formula method is much quicker. However, there is one issue with Newton-Raphson, is that you have to be able to differentiate the function. So there's, when anything that works quicker, there's usually there's sometimes a catch. Like Simpson's rule, you have to have the right number of an odd number of data points, otherwise you can't use it. Newton-Raphson's method, fine, as long as you can differentiate the function. If you can't do that, then you have to resort to the bisection method. But it's fairly easy to put a spreadsheet together and spot the changes from positive to negative and get a spreadsheet or a piece of software to actually do that very quickly. That's what your calculator is doing. Okay? So that's finding the roots of a quadratic. Okay? Now, check that with the quadratic formula. So checking the result that we got through bisection method using the quadratic formula to the same number of significant figures, we get the same result. Okay, and that is believe you me, how your calculator is doing it, probably using Newton-Raphson's, but could quite easily also be alternatively be using the bisection method. But it can do these calculations by getting computer very quickly, blink of an eye kind of thing. Okay. What we're going to do now is have a look at one that's slightly different in terms of, we're going to use the bisection method, or you are, use the bisection method to determine the positive root of the equation x plus 3 is equal to e to the x. Now, in this case, what we're looking for, there's the graph of y equals x plus 3, one half of the equation, plotted, and there's the graph of y is equal to e to the x plotted. Yeah? And what we're looking for is the value of x at that point where they cross. So that's the result we're looking for. Yeah? Now, first thing I need to do with this type of thing is equate that function to 0. So we want to get everything, what equating to 0 means is move everything to the left hand side so that the function is equal, you've got a function equal